characteristic P invariants.
Thanks so much, and thanks a lot for the invitation. All right, so we saw these two invariants. One, the low canonical threshold in characteristic 0, and the Fpo threshold in characteristic P. Right, so the low canonical threshold was defined in terms of an integrability condition. You can also think about it slightly differently. So you can think of it, you can define it in terms of values of the function on various divisors that you have over the variety. And then the existence of a resolution of singularities, of this embedded resolution, gives you a finiteness result, which tells you that, in fact, you can compute this on the resolution. For example, in particular, you get this rationality. So what happens in characteristic P is that, as Kevin pointed out, right, we don't have resolution of singularities. But I think this is not why somehow one looks at this Fpo threshold. Right? I mean, one can still define low canonical thresholds also in characteristic P. The fact that we don't have resolution of singularities says that we don't know whether these are rational, but that's a different issue. So really, the Fpo threshold is a different beast. So somehow it captures different sort of information. So what's very interesting is that it turns out that the two invariants defined by different methods, in fact, satisfy very similar properties. And the most interesting thing is that somehow the properties that are quite subtle in characteristic 0, and for example, you use vanishing theorems to prove them, in characteristic P actually are very elementary for the Fpo threshold. So this is one interesting aspect of the subject. But actually what I'm supposed to talk about is something else. So I want to talk about the comparison between what happens when you go from characteristic 0 to characteristic P via reduction mode P. Right, so let's fix the setting. All right. So let's say I'm going to fix some x to be a smooth. So the ambient variety will always be smooth. So smooth variety. And now, depending on your taste, so let's say it's defined over the rational numbers, but this is not very important. I mean, if you prefer, the more natural setting is to work over the algebraic closure of Q or any field of characteristic 0, in fact. But it should be defined in characteristic 0. Okay, and we want to study singularities for some divisor D. So D will be an effective divisor on X. All right, so we are in characteristic 0. We can choose. I'm going to take one of these embedded resolutions of singularities. So let's say pi from, let's say, some y to x is an embedded resolution of singularities of D that showed up in Rob's talk. Right, and then once I have this picture in characteristic 0, right, so I can compute, for example, the low canonical threshold, but also these other invariants that have not been defined and which I'll explain later, the multiplier ideals. Right, so from this picture you compute this LCT of x comma d, also the multiplier ideals. So these are some ideals on x depending on some parameter, right? Exactly like the ones that showed up in Kevin's talk, the test ideals. So this will depend on some parameter t. All right. So now what you want to do, you want to reduce to mod p. Right? So now we'll restrict to positive characteristic. All right, so what I mean by this is the following. So in the simplest case, when you work over the rational numbers, you just get rid of the denominators. All right, so choose model of the denominators. So choose model over Z for all these, clearing denominators. So of course, if I work over Q bar, or if I work over some arbitrary field of characteristic 0, I might need to work not over Z, but might need to go over some finitely generated algebra over Z. But I won't worry about these subtleties. Algebra over Z. All right, and once I have this, then I can just really reduce mod P. So once, for example, once I choose the model over Z, I'm going to choose some prime P. Typically, it will be large enough. Right? So for P large enough prime. And the reason why I want this to be large is that I want everything that happened in characteristic 0 to still go carry through in characteristic P. Right? So I want, for example, that the reduction mode P of X is smooth. I want that this is still a log resolution, embedded resolution of singularities, also in characteristic P. So precisely because of this, I will have no problems about the existence of resolutions in characteristic P, right? Since everything comes from a setting that I understand in characteristic 0. So for prime, we reduce mod P to get a similar picture over Fp bar, or over Fp, let's say, over the finite field P elements. All right, so then what I want, in particular, I can restrict, for example, these ideals. And I want to compare the invariance from characteristic 0 to the invariance in characteristic P. So most of the time, I'll just stick to the numerical invariant, comparing the low canonical threshold in characteristic 0 to the Fpo threshold in characteristic P. Right, so I get a similar picture over Fp. So what I'll write xp and dp, and for example, I'll have this multiplier ideal mod p and so on. Also, the question is compare the value of the invariant in characteristic 0, for example, the low canonical threshold of D with the Fpo threshold of X. Okay? And now let me remind you the example that Kevin discussed. Right? So in some sense, this will be the motivating example, at least the first one. Then I'll talk about another one. Right? So recall the case of the cusp. So f is x squared minus y cubed over the integers. Right, so now, as we've seen, the low canonical threshold is computed using a resolution of singularities for this thing. By the way, the resolution of singularities stays the same in arbitrary characteristics. So there is no problems restricting everything and working over any prime p. Right, so we know that the low canonical threshold. So what I was saying is that the same resolution holds over in arbitrary characteristics. So there are no subtleties about, I mean, if you just take that sequence of blow up, just in this case, in this particular case. So the low canonical threshold is equal to f, of f is equal to 1/2 plus 1/3, so it's 5/6. And then for the Fpo threshold, of Fp, so we got these different values. So we have 1/2 if p is equal to 2. We get, what was it, 2/3 if p is equal to 3. And then there are, all right, so let me move here. So there are the interesting situations when p is larger than 3. So you get 5/6 if p is congruent to 1 mod 3 and p larger than 3. And it's 5/6. It's the same thing. P is larger than 2, right? So mod 3 or mod 6 is the same. So and 5/6 if, 5/6 minus 1/6p if p is congruent to 2 mod 3. All right, so these are the two. And again, what I claim is that essentially every phenomenon that shows up in this picture can be seen in this example. Okay, so I guess Kevin has already alluded to what happens, but now let me state these as theorems, respectively, as a conjecture.
For low primes, right? But it's not.
No, in this particular case, no, it's not. Basically, exactly the same blow-ups give you the resolution also in this case, because in fact, it's really something toric. Basically, you just blow up some very simple. Essentially, it's the resolution of the ideal generated by x squared and y cubed, which is toric. So
You're over a perfect field, right?
oh, in characteristic P, yeah. I'll always be over FP. All right, so here are the main two results. So they are both due to, I mean, in this version, to Hara and Yoshida. So the first one says that for P large enough, we always have one inequality. So the log canonical threshold of F is greater or equal than the Fpo threshold of Fp. So you see that in some cases, I mean, the Fpo threshold can go down. It can go down quite a bit, but anyway, you always have this inequality. So this is actually not a hard theorem. So I'll explain the argument how you see this later in the talk. The deeper thing is what happens when you let P go to infinity. So also to Hara and Yoshida. So this says that the limit when P goes to infinity for the Fpo threshold of Fp is equal to the log canonical threshold of F. And finally, the main open question in this setting is actually whether you can get equality or not. So this is what I'll call conjecture 1. This says that there are infinitely many primes P such that you have equality, such that the log canonical threshold is in fact equal on the nose to the Fpo threshold. Okay?
Actually, many primes.
That's right. So given this setting, I guess, of course, the set of primes, so given the pair x comma d.
So this is your conjecture with Srinivas? Or?
No, so I think maybe it was a conjecture with Takagi and Watanabe, but I think, I mean, basically this sort of phenomenon appeared before. So, all right. Okay.
In theorem 2, when you write limit, it's like a lim sub or something.
No, it's really a limit. Right?
Here. Oh, yeah.
It's also a limit, right? So,
sorry.
all right. So now let me discuss another example. So in some sense, this example is a little misleading because it looks like the picture is very simple, right? It really depends just on a congruence class of P. So let me discuss another example, which is actually the example that Rob mentioned, right? So as Rob said, right? So in the geometrically, that the case of a cone over a smooth projective variety, it's actually very simple. It's just governed by multiplicity. On the other hand, in this sort of arithmetic setting, actually, it's very subtle. Okay, so let's look at that example. So in fact, I'll stick to one special case. So suppose that, so let f be a polynomial. So I'm going to take the polynomial ring in n variables. And I'm going to assume that this is homogeneous of degree n.
So the same degree as number of variables.
The same degree as the number of variables. Right, and such that it has an isolated singularity with an isolated singularity at 0. Right. In other words, the corresponding projective variety is smooth. Right. So this defines a smooth hypersurface in P n minus 1. And the condition on the degree is such that, in fact, this hypersurface is Calabi-Yau. All right, so let's say hypersurface, let's say this is Y. And in other words, the canonical class of Y is trivial. Okay? All right, so now if you remember the first lecture this morning, right? So what you do is, how do you resolve this? You just blow up the point. All right, so so the resolution is given by the blow up of the, of course, it's the resolution for the hypersurface defining by F. Right, and you have two divisors, right? You have the exceptional divisor and the proper transform of my of the divisor D. Right, so I have here d tilde, and E is the exceptional divisor. All right, so now a simple computation tells you that.
You have to keep blowing up, right?
No.
No, this time you don't need.
Oh, yeah.
Right, so you have the intersection of the two divisors, d tilde and E, is exactly the hypersurface Y, which is smooth. So this is really a divisor with simple normal crossings. Right, so if you use by the definition in terms of the resolution, so the log canonical threshold of x comma d, so you have is the minimum between two things. The first thing, right, so d tilde appears with coefficient 1, but also the coefficient of the relative canonical class is 0 plus 1, you get 1. And what about E, right? So the order of vanishing of the hypersurface along E is the multiplicity, which is n. So now the coefficient of E in the relative canonical class is n minus 1. So if you add 1, you get again n, right? So it's a minimum between 1 and 1, so it's equal to exactly 1. Okay, so again, from the point of view of singularities, this is an extremely simple case. So now what I want for what, so the question is, when is fpt of xp and dp? Okay.
That should be minimum between 1 and n, right?
Minimum between 1 and 1.
Oh, 1 and 1.
Right? So again, so what both ratios are equal to 1. Yep, it's n over the degree in general. All right, so now let's try to interpret the definition of the Fpo threshold in this case. Right, so I'm not going to write the definition exactly as Kevin wrote it, but it's easy to translate by the definition in the following way. So by definition, we have that fpt of xp and dp in this case is greater or equal to 1 if and only if the following holds. So whenever I take f to the power p to the e minus 1, this is not in the ideal generated by x1 to the p to the e, xn to the p to the e. Okay, so I didn't divide by p to the e, but it's exactly the same property that Kevin had. All right, but now note, I mean, how does this polynomial look like, right? Let's say modulo this ideal. So remember that the degree of f is exactly n, right? So it's homogeneous, so this has degree n times p to the e minus 1. So there is only one possibility for the monomial in here not to be in the ideal generated by these guys, right? So note that f to the p to the e minus 1 can always be written as some coefficient ce, so that monomial is just the product of all the variables xn to the p to the e minus 1. So this is congruent with this one, modulo this ideal. All right? Okay, but then a simple computation tells you, I mean, how to relate the various CEs. So CE here is just in the ground field in FP.
The ring mod in that degree is just the quotient is one-dimensional in this case.
That's right. In modulo this ideal in this degree. Right? So that's the only thing that you have. Right, so it's now an easy computation. Tells you that, in fact, CE is just equal to C1 to the power 1 plus P to the E minus 1. Of course, since these are actually elements in Fp, you can simplify this further, but let me not do that. So what I care about is that this is non-zero if and only if C1 is non-zero. Right? So what's the conclusion? Is that the FPT of this, let me write, Fp is equal to 1 if and only if C1 is different from 0. Right? So basically what you have to do, you have to take the p minus 1 power of the polynomial f, and you have to look at the coefficient of this monomial x1, xn to the power p minus 1. So it's something very, very concrete. Now what does it mean geometrically? So geometrically, this is equivalent to the fact that if you look at the Frobenius action on the top cohomology of the structure sheaf, so let's see, so my hypersurface y is in Pn minus 1, so it's of dimension n minus 2. So I look at n minus 2. So this is Zariski usual sheaf cohomology of y, of course, p, OYP. So if I look at this action on itself, so remember, so this is a Calabi-Yau hypersurface, right? So O is the same thing as omega, right? So this top cohomology is one-dimensional. So what I want that this is not 0, right? So this is not 0, non-zero. All right, so let me translate the conditions that we had before in these terms, in terms of the cohomology. No, sometimes it's 0, sometimes it's not 0.
Well, what?
It could be, it's a one-dimensional vector space.
So the action of the Frobenius might be just 0.
Oh, the action of Frobenius.
Yep, that's right.
Oh, it's an isomorphism.
No,
Really?
so this is sheaf cohomology. It's not the Elladic cohomology.
You can have super singular.
Yes, that's right. Okay, so anyway, let me translate this condition in these terms. Right. So first of all, where does the Frobenius action on cohomology come from? Right. So you have a map that goes from the structure sheaf OY. Let me write OY instead of OYP. Right. So so F is right the morphism. Right. You have a morphism from OY to F lower star OY. Of course, F lower star OY is just OY. Right. But this map takes something to its pth power. Right. So this takes U in here to U to the P. All right. So now I have the same thing. I'll write the same on projective space. So this is Pn minus 1. F lower star OPn minus 1. Okay, so the kernel of this thing is OPn minus 1 of minus n. So this is a standard short exact sequence. So here I have F lower star OPn minus 1 of minus n. All right, so now let's try to identify this thing, right? So this is again Frobenius. All right, so what are the maps? This is just multiplication by f. This is also multiplication by f. Right, so now if I go this way, what am I doing? I'm multiplying with f, and then taking everything to the pth power. Right, so now in order to get the same thing when I go this way and this way, I have to multiply here. What is this map? It takes u to f to the p minus 1 times u to the p. Right, you first take the Frobenius and you pre-multiply with f to the p minus 1. All right, so now if you look at the long exact sequence in cohomology, the top cohomology of OY is the top cohomology of O of minus n, right, which is the again, it's one-dimensional. But what this tells us what is the action of the Frobenius on this cohomology. Right? It's given, it's induced by this map. So we have h n minus 2 of y p and O y p is isomorphic to h n minus 1 of p n minus 1 and O of minus n. Right?
Dimension of y.
So y is n minus 2.
It's hyposurfacing p minus 1.
All right, and this, the Frobenius here is induced by this map. So now let's try to describe, right? We have the check computation for this guy. Right, so the check computation. So check description of cohomology.
Yeah, but I want to see it.
All right, so what is this? Right, so this is, so I'm looking at the localization of the polynomial ring at x1, xn, modulo, well, the image of what I get when I forget one variable, right? I localize it all but one, xi, xn, and I'm taking the degree 0 part. The degree minus n part. All right, this is for this minus n. All right, so of course this is just a one-dimensional space. So let's see what Frobenius does on the generator. All right, so Frobenius, so a generator is just the class.
Yes.
So S is my polynomial ring. I guess it's not. It's the polynomial ring in x1 up to xn. So S is this. I guess it's Fp now. I guess I should put Sp, but. All right. So I'm looking at the generator, which is the class of x1 up to xn. All right. So now let's see. What does this do to it? Right? You take the p's power and you multiply by f to the p minus 1. Right? So Frobenius takes this guy to f to the p minus 1 over x1 to the p, xn to the p. And now you see what's the condition for this to be 0. Right? 0 if and only if this lies in the image of this guy. So basically it means that if I expand this as a monomial, right, each monomial kills one of the guys, either x1 to the p or xn to the p. Right? So this is 0. In the cohomology, if and only if, right, f to the p minus 1 lies in x1 to the p. The ideal generated by these things, right? Which is exactly what the claim was. Right? So this. Okay. All right. But somehow this shows that somehow there is something a bit subtle going on. At least if you know the picture for elliptic curves. Right? So now let me recall what happens for elliptic curves. In fact, this is the only case that's well understood from this point of view. Okay, so special case when n is equal to 3. So then y is an elliptic curve. Okay, so what's known in that case? So first of all, this condition has a name. So then we see that the fpt of fp is equal to 1 if and only if yp is what's called ordinary. Okay, but I mean, this is just a name. Otherwise, it's called supersingular. All right, but one understands very well in this setting for which primes p the reduction is supersingular and for which it's ordinary. I mean, at least the distribution of such primes. So for elliptic curves, from this point of view, there are two. There is a dichotomy which is between the ones that have complex multiplication and the ones that don't have complex multiplication. Right? So there are two cases. It doesn't really matter what it means. So if y has complex multiplication, so what this means is that more automorphisms than expected. Okay, then, so what this means is that if you describe the lattice of y in terms of, right, in the complex numbers as 1 and some number tau, so tau must belong to a degree 2 extension of Q. Right, so this corresponds to some degree 2 extension. So then the behavior depends on whether the prime P splits when you go to K or not. Right, so if you go from Z to the ring of integers of K, it's a degree 2 extension, so either the prime becomes a product of two primes or it stays prime. It's inert, right? So if P splits in K, so then Yp is ordinary. And if P remains prime in K, then Yp is supersingular. Okay, but basically this, about for half of the primes, one happens, for the other half, the other one happens, right? So each of them holds roughly with density 1/2. So each of the two happens for roughly half of the primes. So if you want, it's a behavior similar to the one for the cusp, right? Where you had, for half of the primes, you had 5/6. For the other half, you got something different. A more subtle case is when y does not have complex multiplication, does not have Cm. And you should think of this as a generic case, right? So most elliptic curves have this property. So then what happens is that, so it's a result of Elkis, because I started with elliptic curves over Q, that there are infinitely many supersingular reductions. However, it was proved by Serre that these have density 0, such P have density 0. So in some sense, from our point of view, this is a better situation, right? Because we have, for almost all of the primes, they satisfy the properties that we want. On the other hand, the bad news is that somehow the set of primes is actually a bit mysterious, right? I mean, you have something of density 1, but such that the complement is still infinite. So it's a bit hard to understand. So what I'll explain later is that while you have this complicated picture, there is always some number field, such that if P splits completely in that number field, you have ordinarity. Okay, so that's more elementary, so I can explain.
P has density 0, such P is in the set of primes themselves.
That's right. That's right.
Not in the integers.
Yep, it's a set of primes. That's right. All right, so now let me state another conjecture, which is somehow the arithmetic counterpart. I mean, the global counterpart to the previous conjecture. Right, so what I claim is that something very similar to this example holds all the time. So, all right, so conjecture 2, to which I'll refer as weak ordinarity conjecture, says the following. So suppose that, so now it's a different, maybe I should use a different letter. So let's say if y is a smooth projective variety over Q, or let's say Q bar. I think it's better. Okay, so then there are infinitely many prime. There are infinitely many prime reductions such that if I look at the action of the Frobenius, so I should put some dimension. So let's say dimension n. So if I look at the action of the Frobenius on the top cohomology, so this is yp OYP. So this is semi-simple. I mean, you just think, I guess, just think it's an isomorphism. It's semi-simple. Okay, so now this is not just a one-dimensional space. So this is, in general, can have higher dimension. So what I really want is that the action of the Frobenius is an isomorphism on this one. Okay, so this is the analog.
What you really want is what? Here.
That it's an isomorphism. Okay, so usually one has to be a little careful since this is not necessarily linear, but let's not worry about this. So that's why one says semi-simple instead of isomorphism. Okay, so that's the conjecture.
Is there a prime number theorem for these primes? Like, is there the density is 0, but it goes to 0 at a certain rate, like in the prime number theorem?
I don't know about that.
I mean, basically even proving that there are infinitely many was a deep theorem. So this was Elkis's thesis.
The theorem. Then we want to go to the next.
Yeah.
Right.
That's right.
Can I replace the word semi-simple with bijective?
Yes, that's fine. At least if you go over Fp bar. That's right. So
even okay, so not over. And it's going to be over a finite field, right?
Yes. So this is a vector space over a finite field.
And since that's perfect.
Yes,
Yeah,
that's right. But that's right. No, you're right. Yeah, I can say it's bijective. All right. So the theorem, which doesn't prove any statement. So this is a joint thing with 3 plus. Is that in fact this conjecture, so conjecture 2 implies conjecture. So okay.
The supersingular only applies to curves with complex multiplication.
No, so supersingular.
Finish up there, and then you have the next sentence. Are they supposed to be following, or is this just a new discussion?
So supersingular, I'm afraid, let's see. No, supersingular always, for elliptic curves, always means exactly that the Frobenius action on H1 is 0. But this is a notion that applies to elliptic curves. Okay, so in general, one has to be careful how to define it when this has higher dimension.
Well,
So what I was saying here is that when you have complex multiplication, about half of the primes are ordinary primes, half of them are supersingular, depending on this behavior.
and what's the general definition? In this Elkis theorem, you're talking about general elliptic curves, right?
Yes,
Okay.
that's right.
And then what's the definition of supersingular?
So supersingular is the same definition. So it just means that once I reduce it mod p, right? So this is supersingular if the action of the Frobenius on H1 is 0. For elliptic curves. This is just for elliptic curves.
She says the same definition.
No, yeah, the definition has nothing to do with which case I mean. So again,
This is not a definition.
this is not a definition. So this supersingular
Calculation.
means it's not ordinary, right?
It's a statement.
What's the definition?
It's not ordinary.
What's ordinary?
So ordinary means that the Frobenius action is non-zero on H1. All right, so 2 remarks. Is that in fact, one expects that at least a large part of the primes that satisfy either of the 2 conjectures should have some arithmetic meaning. So the most optimistic thing is the following. So one expects the following. Is that there is some number field K such that whenever P splits completely in K, we have that, for example, the assertions in both conjectures hold.
Assertions in, let's say, conjecture 2.
This is for X.
Or conjecture 1. Okay, so it's not an arbitrary set of primes. So again, if you think about the case of elliptic curves, even in the case of when you don't have complex multiplication, what this says is that, well, all the primes of ordinary reduction form a strange set, which is large but somehow hard to understand, but there is a part of it that comes with a certain arithmetic interpretation. So these are the primes that split in the number field as a product of the right number of primes. Okay? So for example, by the way, so what happens for the case of a cusp? Right? So always this sort of condition when you have P congruent to 1 mod something, this is precisely the condition that something splits completely in the cyclotomic field. Okay? So somehow it matches well with this expectation. All right, and one last comment is that, in fact, very little is known about the conjecture, about conjecture 2. So that's probably very hard. So basically, the cases that are known is okay for curves genus G less or equal than 2. It's also known for abelian surfaces and for K3 surfaces.
Have genus 2, you say?
Genus 2 is okay. Yeah, so basically genus 1 and genus 2. Any questions? All right, so what I want to do rather is, I'm not sure, I don't have that much time, I guess just half an hour. So maybe I'll take 15 minutes to explain one result, which is very partial, but for example, it covers conjecture 1 for elliptic curves, just to give you some intuition where such a number field could come from, right? So where, I mean, there should be some place the number field should show up, okay? So I'll prove something particular just in the case of curves, and it will also give you some feeling for the kind of techniques that one might need to use to prove something like this in general.
Is the expectation known for elliptic curves?
Yep, I'll explain. Yeah, that's right. So this is okay. All right, so now let's prove the following. So let's say that X is a curve of genus G at least 1. Oh, of course, smooth curve. I guess my previous notation was Y, but anyway, let's. All right, so this is a smooth curve of genus at least 1. So then the assertion is that there is some number field. Okay. Such that if P splits completely in Q, then, well, you don't have what you want. The action of the Frobenius is not necessarily bijective, but at least it's not just 0. It's not nilpotent. Right? So then the action of the Frobenius on H1 for xp and OXP is not nilpotent. Okay, so for example, for elliptic curves, this is enough, right? Basically, this tells you that it's not 0, and therefore it's bijective. But this is actually very close to somehow to the optimum thing that one can do at this moment with these techniques. So what one can do, in fact, is one can do a little bit better. One can show that if G is at least 2, in fact, you can get at least something of dimension at least 2 on which this is semi-single. Right? So in particular, this covers the curves also of genus 2.
Can you explain the meaning of this, just the quantification? there exists a number field such that if
So there is a number field with the following property, right? K such that the following holds. If P splits completely in K, then this is not nilpotent. Right? So by the way,
before you give me the curve, you give me the number field?
no. So first of all, I fix the curve, right? So and I'm saying that there is a number field K, depending on X, of course, such that this property holds.
Okay.
So by the way, right? So there is a classical theorem due to Chebotarev, which says that there are infinitely many such primes which split completely in a number field.
Right? So this in particular proves.
There are infinitely many things.
Other questions?
Not nilpotent means semi-simple or?
No. So not nilpotent just means that it cannot be completely nilpotent. Right? So the semi-simple part has dimension at least 1.
I don't quite understand the logic. I mean, given a curve defined over P,
No, the curve is defined over Q.
the field
Yeah, there is.
with the following property,
Yeah, so the curve is not over. Right, so the curve is over Q. Right, so,
defined over something, yeah.
And written characteristic 0.
right, so I always start in characteristic 0.
Curve over Q.
Yep.
There exists an algebraic number field.
Yeah, such that the splitting of P in this number field implies what I want.
Which P to get this Frobenius action? Which P is no, not. So you're saying because we characterize
All right. Okay, so let's prove this.
controlled by one number field.
Oh, I see.
All right, so where does the number field come from? Okay, so I'll do the following. So fix L to be a prime. Some restrictions will come later, but there are basically, I have to exclude finitely many possibilities depending on the genus. So we'll assume this, but that doesn't make sense to describe it now. And take A.
Can I formulate the statement of proposition again? Given the curve defined over Q, consider all these problems, all these Frobeniuses acting on H1, and we want to know for which reductions are nilpotent and which not nilpotent and which ones are not. This is decided by.
No, it's not decided. It's not decided. There is only one implication.
Wait, let me finish. Then you can tell me. Then there exists a number field such that you look at the prime in that number field and ask if it splits completely, and that tells you the answer.
That's right, but it's only one implication.
Huh?
Only one implication. If it splits completely, then it is not nilpotent. The converse is not true.
Okay, but I just. Yeah. So you can ask all these questions before the number field comes.
Yep, exactly.
It tells you the answer.
Yep.
One way.
That's right, exactly. All right. So let's look at this abelian variety, which is the Jacobian of X. Right, and I'm going to look at the scheme A of L of L torsion points. Right. Okay. So this is, of course, as a scheme is defined over Q, but in fact, what I want it to become trivial, to be a union of points. So this is where the number field comes in the picture. So let K over Q be such that this, how should I say, all the points such that this is a union of K.
So basically, you're adjoining coordinates.
I adjoin coordinates for the points in this. If I look at the points in Q bar and I adjoin the coordinates. That's right. All right. So now what I claim is that what I want to prove is that if P is greater or equal than 0, but in fact this bound will also be very explicit, right?
Explicit. Depending on G.
Then, and P splits
Completely. In K.
Well, of course, I also want that the reduction of X is, and XP is smooth. Good reduction. So then the Frobenius action on H1 is not nilpotent.
It's
It's not equal.
All right, so of course, let's suppose that it is nilpotent. And let's try to get a contradiction.
Okay.
So how am I going to use the fact that it's nilpotent? So this implies that the trace is 0. All right, so now there will be a bunch of ingredients. So the first ingredient is a fixed point formula for coherent cohomology, due, I guess, first to Fulton, and then there are various fancier versions due to Katz and the linear. Right, so there is a formula called the fixed point formula, which says the following. So now we are over Fp, right? By the way, right? So the fact that P splits completely, right? In particular, we are over Fp. So this says the following, that if I look at the number of points of xp over Fp, right? So this is an integer, but what the formula says is that you can compute it mod P from the alternating sum of traces on coherent cohomology. Right? So this is equal to the trace, or so I guess this is an integer, so I should put mod P is equal to the trace of the Frobenius on H0 of xp OXP minus the trace of the Frobenius on H1 xp and OXP. Okay? So this is in fact rather elementary, and it's a beautiful proof. So, but anyway, all right, so we have such a formula. So there is no mystery about the trace of the Frobenius on H0, right? This is really just identity. Yes?
So what sort of a gadget is the... I mean, so you said that the Frobenius action is not linear in general, right? So...
Well, in this case, I guess, in this case, it is linear, right? So in general, because we are over Fp, that's right. So otherwise, basically, you work over Fq, and you are supposed to work with powers of the Frobenius to make them linear.
Yeah, but if it's not linear, I don't know what the trace means.
Yeah, that's right, that's right. You are supposed to take the suitable powers to make them linear.
Linear? Over the field.
That's right. It's not linear over the field. All right. So this is the first trace is 1. The second trace is 0 by our assumption. So this is equal to 1. Okay. All right. So now what we know is that the number of Fp points mod P is equal to 1, right? Okay. So now you can use another fixed point formula. So there is this Grothendieck-Lefschetz fixed point formula. So now we'll go and interpret the information from, instead of coherent cohomology, on Elladic cohomology. Right? So there is the Grothendieck Lefschetz. That's right, I guess. Okay. All right, so what does it say? So this says that the number is actually equal, so the number of Fp points on xp is equal to the following. So now I'm going to look at traces on Elladic cohomology. So is the trace Frobenius, all right, let me not write all of them. So is sum I from 0 to 2 minus 1 to the I, the trace on hi tau of x p. I guess really I have to go to fp bar.
And with, let's say, Elladic. Q over 0.
Okay, so that's the formula. All right, so now here again, as in the previous case, two of the terms are very easy. So on h0, again, this is equal to 1. And on h2, this is equal to p. Right, so this is in fact equal to p plus 1 minus the trace on h1. Right? Okay, so now finally the last ingredient is this wave.
On the H2, right?
Sorry, P is on H2, that's right. So the last ingredient is the Weil bound on the trace on H1. Right, so this is the information that's equivalent with the Riemann, what is it? The Riemann property for curves over finite fields. Right, so this is one of the properties proved by Weil. So Weil proved the following: is that the difference between this number xp of fp and p plus 1 is in fact bounded above by 2g times square root of p. Okay? Of course, there are versions over fq. But all right. So now what can we conclude from this one? So what do we know? So we know that this expression, the number of xp points with values in fp, is congruent to 1 mod p. So I claim that this forces this expression to be equal to 0. Right? Because if it's not, then what will it be? It will be 1 plus p times times something else. Right? So this. All right. So again, let me remind you. So this guy here. We prove that this is congruent to 1 mod p. Hence, what I claim is that in fact, xp and fp must be equal to 1 plus p. Right? Because otherwise, what you get is that p times some multiple, which is less or equal than 2g times square root of p, right? But this is false when p is large, right? So this is the bound on p that you want. So this is false for p large. Okay. All right. So what does the Weil bound tell you? So it says precisely that the number of fp points is 1 plus p. So now if you go back to this formula, it tells you that the trace also on H1 is equal to 0. Right? So basically, all this work was in order to go from the trace on coherent homology to the trace on Elladic homology.
Splits.
No, I haven't used that. So that comes right at the end. We are basically there. Because I have to actually tell you something about H1. Right? So the conclusion is that the trace
Frobenius from H1
with real coefficient
is equal to.
Okay. All right, but what I want to do, so I'm not going to compute this whole thing on the whole Elladic homology, but I'm going to compute it mod L. So I'm going to compute it with coefficients in FL, right? Which is basically just computing this number mod L. Right, so however, let's say, so now I'm going to look at H1 again of x over fp bar with coefficients in FL. Right, and this is simple to describe. So first of all, it's the same thing as for the corresponding abelian variety.
It's H1 et al.
For the abelian variety, for the Jacobian. Here. Bar with coefficients in FL. And this is simply the number of
What?
This is given precisely by the L torsion points on the abelian variety over
The FP bar?
I mean, as a group, is simply Z mod L.
2G.
Okay. But now comes the point. So we assume that P splits completely in this number field. So what this means is that this scheme A, when I go over FP bar, becomes trivial. And not only that, I mean, it's a union of points, but also the Frobenius section becomes trivial.
Awesome.
What do you mean when you say the Frobenius action becomes trivial? What do you mean by
It means that it becomes the identity.
identity?
That's right. Let me write it. So since P splits completely in K and AF L consists of k consists of k points. I mean, basically, it's the same as the Frobenius section on one point. So this implies that the Frobenius section on H1 et al. Of x Fp bar with coefficients in Fl is the identity. Okay, so in particular, its trace is what? It's 2G. Right? So this is a 2G dimensional space. Okay, but now we have our contradiction. Right? So we have an element of ZL, which is 0 and which is congruent. So this implies that 0 is congruent to 2G mod L. Right? So if we choose, I mean, I told you that at the beginning that I'll have to make to avoid some pathological cases. So if we choose L such that L does not divide 2G, we have a contradiction. Okay. So. Sorry. Yeah. That's right. In principle, it looks like you have a lot of freedom, but I'm not sure what you could do with it. So, but right. I mean, still, for example, like the case of elliptic curves with complex multiplication, tell you that basically you cannot have more than half of them, half of the primes. But anyway, so that's basically almost the best possible result. So actually, you can go also to curves of genus 2, but with a lot of work somehow using deeper stuff about crystalline cohomology. But then, anyway, I hope that at least this shows where the number field might come in the picture. Any questions? All right, so now I'm going to change gears, and I want to tell you a little bit about the proof of the theorem.
So we let P equal L now or something?
No, L is always, sorry, I should have said P is always different from L.
P is always different from L.
Right. Because I don't.
Where does the mod L come from here?
Because I computed it in FL, right? So, so the other one is the projective limit of all these guys.
Yeah.
All right, so it turns out that, like in what Kevin did.
Can I ask a philosophical question? Sure. This Elladic stuff is sort of like the topological Lefschetz fixed point theorem, right? And what's this theorem like? This coherent cohomology one?
I don't know how to think about it in the same way. I mean, again, it's some sort of avatar of the same.
Lefschetz fixed point theorem or something?
If you can reduce
There is that.
Something like a Tier-Bot. I don't know if you can think of it. I mean, in some sense, yeah, it's some sort of coherent avatar of this sort
of the same phenomenon.
What?
It's some sort of coherent version.
Coherent
right?
version.
But,
I don't know.
Yeah, all right.
all right. So now,
Sketch.
conjecture 2.
False conjecture.
Remind us what the conjectures.
Yeah, right.
Yes, so the conjecture 2, this is weak ordinarity. So this is the geometric thing, weak ordinarity. And this one is the assertion about Fpo threshold and low canonical threshold. But in fact, I'll prove something else. So I'll show that conjecture 2 implies that there are infinitely many P's such that, well, not only that the numerical invariants are the same, but in fact, also if I take the multiplier ideal of x and t times d mod p, this is the same thing as the test ideal
Of xp and t times dp.
for all t. So now if you remember, so from what Kevin was saying, right, so you can identify the Fpo threshold as the place where the test ideal becomes not the whole thing, not the structure sheaf. Exactly the same thing happens for the multiplier ideals. And basically, in particular, this equality implies that the low canonical threshold is equal to the Fpo threshold. Okay, but this is a better statement. And another reason why I think it's a better statement is that, in fact, this fact, the fact that you have infinitely many p's with this property, in fact, implies conjecture, the weak ordinarity conjecture. So in fact, if I put this stronger statement, then the two conjectures are in fact equivalent. Okay. All right. So let's see how we want to prove this. All right. So the first remark is that you remember that when Kevin described the test ideals, so these are simpler to understand if T has denominator a power of P. And again, since I want to have the equality for all T's, I might as well deal just with, it's enough just to prove it for such rational numbers. All right, so in fact, it is enough to prove this when T is some, let me write A, B to the E. Okay? Because these are dense, and I mean, by the semi-continuity properties of these invariants, you get it for all T's. All right, so now so I'm going to write for you a slightly different way of looking at Kevin's definition. So Kevin worked on the affine space, but since I want to compare what happens on my X and on the resolution, I really need somehow to have a more global way of looking at the multiplier ideal, the test ideal. Right, so what is the test ideal for X? And let's say XP, I guess I should put an A over P. Maybe I won't worry about putting the P's. It can be described as follows. So the key gadget in this setting is this trace map that, again, Kevin alluded to. Right? So we have, since X is smooth, we have this morphism that goes from the push forward of omega to omega. Okay, so I think for the all right, so let me tell you what this does. Right, so in local coordinates, let's say x1 up to xn. Oh, maybe I'll write on this one. Right, so it takes x1 to I1, xn to In, dx1, dxn, to x1 to I1 minus p minus 1 over p, xn to In minus p minus 1 over p dx1 dxn. All right, so it doesn't really matter the precise shape. Of course, what I mean is that this monomial, if some of the exponents are not integers, this is just 0. So the thing to take is that this looks a little bit like taking the pth root of the monomial. It's just that it's done in a slightly non-obvious way. Okay, but the point is that the reason it's better to take it like this is that once you do it like this, it's independent on the choice of coordinates. And then you have this map, which obviously is surjective. All right, so you can think of this in many ways. So it shows up, for example, from the point of view of the Cartier isomorphism. You can think of it in terms of some sort of trace map for duality with respect to Frobenius. But anyway, this is somehow one of the important incarnations of Frobenius. All right, so then if you think about it this way, so then I shouldn't have erased it. All right, so what is the test ideal? I simply take f lower star. Let me write it again. So I have f lower star of omega x mapping to omega x. So I can iterate this thing. I can apply the Frobenius, then I get a map from f square lower star of omega x to f lower star of omega x, I compose it with itself. So let's see. So let's say this is trace E.
Equals omega x in some sense.
Sorry. So this is not. This is a surjective thing, right? So this is a line bundle. It has rank 1. This one has rank p to the dimension of x. But somehow it allows me to go from, yeah. Anyway, so it's a way to relate the push forward of omega to omega. All right. So what I want to look here at is an iterated trace.
Here's a map.
Just that there is a map. All right, so now I'm going to look here at f to the e lower star of omega x twisted by minus a times d. So this is a subsheaf in here. So it will have some image, right? And the image is precisely this test ideal of x and a over p to the e times omega x, right? So the image is always, lies inside this line bundle. So it's always some ideal times the line bundle. Okay, so that's one way to think about the test ideal. But it's easy to see that it's equivalent with what Kevin explained. All right, but in this form, it's actually easy to compare what happens upstairs and downstairs. Right? So now let's say we have a log resolution. So suppose f from y to x is an embedded resolution. And let's write the pullback of d as some divisor e. Right, so I'm going to write the same thing upstairs. Right, so I have upstairs, I have. All right, so now maybe I should worry a little bit where the Frobenius lies.
So could you just clarify the minus a times d, right? So how are the parentheses here? Do you do that before pushing forward or after?
Yes. So everything is.
Okay.
Thanks. All right. So I have the same thing as over there. So I have omega y twisted with minus a times e. Right, and that subjects onto the test ideal of y and a over p to the e times omega y. But in fact, this is one computation that one has to do. In fact, for simple normal crossing divisors, the multiplier ideal and the test ideal are the same. So in fact, this is actually something very easy to describe. So this is O of minus O of, all right, so this is the whole thing is, all right, so it's omega y twisted by minus the round down of A over P to the E. Okay. So basically, so what I'm saying is that this ideal is just, can be written in terms of this divisor upstairs, right, with the usual convention for rounding down divisors, right? So now it turns out that this is exactly the gadget that comes up in the definition of multiplier ideals. So now let's push forward this picture. Right, so apply pi lower star. So I'm going to have, let's see, maybe, let me move. So apply pi lower star. So I have pi lower star. Sorry?
What do you mean by pi lower stars? That F
So pi, sorry, F, but F is a bad notation. Thanks. So this, I wanted it to be. Thanks. All right, so I have pi lower star of F E Y lower star of this expression upstairs, omega y of minus AE. So this will map to whatever I have over here. So it will be pi lower star of omega y twisted by this minus A over P to the E times. Right? But now what's the relation between omega y and omega x? Right? So omega y is the pullback of omega x twisted with this divisor that Rob mentioned, right? So this relative canonical divisor. Okay? So when you push this forward, right, the push forward of omega y twisted by this guy, so this is nothing but really omega x tensored with the push forward of y of the relative canonical class minus the round down of a over p to the e times e. Okay, this is exactly what the multiplier ideal is. So this is the multiplier ideal of x and t times d. This is the definition. All right, so now I want to compare it with what happens. Remember that E is the pullback of D. So by the projection formula, this expression here is nothing but omega x. All right, so I have fxe lower star of omega x twisted by minus a times d. All right, and we know that the image of this guy is the test ideal tau of x and, sorry, t is a over p to the e. And a over p to the e times d, times omega x. Okay? All right, so what's the point? So the key point is that if I push forward the surjective map upstairs, it's not necessarily surjective, right? Push forward is not right exact. So I don't know that the image of this guy is the whole thing. The image of this one is exactly this thing, right? So what you get this inclusion. So this is the inclusion that always holds, right? So the conclusion sorry, I'll finish in 3 minutes. So the conclusion is that we always have the test ideal contained in the multiplier ideal So this is exactly what's behind that first theorem of Hara and Yoshida, which tells you that the low canonical threshold is greater or equal than the Fpo threshold. So this is really nothing but some sort of naturality that comes from these diagrams. Okay, and you also see when you have equality. So equality holds precisely when this map is surjective. All right, so with equality, if and only if the push forward of this map that I'll write, or dagger. This one?
The left one, sorry.
Yeah. So if and only if the push forward of the dagger map is surjective. Okay? All right. So now let me make an assumption. So let's suppose that in fact E is reduced. Right? So I don't have any multiplicities. So as you can easily convince yourself, this never happens. But I'll explain right at the end how you reduce to this computation. But this simplifies things quite a bit. You see what happens here if you look at, so let's look at this dagger map, right? So then if E is reduced, when I take this round down, I mean, this is independent of E. So basically, once I have, right, so the dagger map becomes the following: f to the lower star of omega y twisted by minus AE maps to omega y. And now I have minus the round down of A over P to the E times E. Right? And furthermore, E, in fact, is a divisor that comes from downstairs. When I push it forward, I have the projection formula. Okay, so this part will disappear, will cancel out with something from here. So it will be left, so it will be enough to show that I have, well, not to show, but to have also, that f to the e lower star of omega y twisted by e, right, after push forward, is surjective. Okay, so this is the same map that I got from this one by pushing forward after twisting with something coming from the base. But you see now, all right, so this is a little bit hard to digest. But the point is that let's assume that the sheaves, in fact, have global sections. Right? So then instead of talking about the morphism of sheaves, it's enough to prove that at the level of global sections, this is surjective. And all right, so what are the global sections here? Basically, I have just h naught of omega y twisted by e. But then by third dualities, this becomes the top cohomology of O of minus e. All right, so let's see. So if the sheaves are globally generated, third duality implies that it's enough to have that the action of the Frobenius on h top of O of minus e y and O y of minus e is surjective. All right, so I apply duality, so this should be injective. So non-nilpotent, semi-simple. All right, but now I hope it's kind of clear that you write down some long exact sequences. You can control the action of the Frobenius on this sheaf if you control the action of the Frobenius on the top cohomology of all intersections of the components of E. Right, and this is provided by conjecture 1, by conjecture, the weak ordinarity conjecture. Right, so the weak ordinarity allows to control this. All right, so I'm already over time, so I won't write anything else. So the question is what to do. I mean, of course, I made this important assumption for the computation that the divisor is reduced. So the way to be able to carry this computation in general is to first do semi-stable reduction, which means that you do some base change, some finite base change, which allows you to reduce to the case when you have a reduced divisor. Of course, you put in the picture this finite morphism. But fortunately, so Kevin and Carl Schwid proved that, in fact, these test ideals behave nicely when you have finite morphisms. So then the computation that I explained carries over and you get the case in general. So I'm sorry I went over time.
Well, then let's thank Mircea again. And